So the last team we have today is Jackson State University.
Hello, everybody. This is Rakesh Salunke, and I'm at Jackson State University. We call ourselves the Team Zero because, our collective goal is to achieve net zero emissions, right? But anyway, in my team, I have Abhi Priyo, and I would like to also mention Dr. Sadiq Khan, our advising faculty, who encouraged us to take part in this competition. And I'll let Abhi introduce himself. And by the way, I am a PhD student of geotechnical engineering. Thank you.
Hi, this is Abhipriya Chakraborty. I'm also the PhD student of doing PhD in geotechnical engineering in Jackson State University. So both of us actually from a different field of engineering. We are doing the PhD in geotechnical engineering, but it's a challenging job we have done. Let's see what we have done. Okay, thank you.
Stella, we are ready to see the video.
So yeah, you can we can see the presentation right now.
Hello, this is Rakesh Salunke.
Hi, this is Abhipriya Chakraborty.
We are Team Zero, and we are from Jackson State University in Jackson, Mississippi. In this presentation, we will talk about how we evaluated EPA's gas emission model, LANGEM, and also we'll talk about how we explored different methods of gas emission estimation. Landfills are home to all human-generated waste, and landfills are characterized by the types of waste deposited in them. For instance, industrial waste, hazardous waste, green waste, and municipal solid waste. The municipal solid waste, or MSW, is made up of organic waste or food items, garbage such as paper and packaging products, and plastic wastes. The anaerobic decomposition of the MSW generates methane. Landfills are one of the largest sources of methane across the United States and across the globe. A typical landfill cell system is represented in this schematic. The important components of a landfill cell system are, first of all, the liner, which is at the base of the landfill cell, followed by the leachate collection system. And then the waste is placed in layers and it's covered by daily and weekly covers. The cover system is basically made of the local soil type. For instance, in case of Central Mississippi, it is Yazoo clay. And finally, the gas control or gas collection system that collects the methane and the landfill gases emitted and either disposes it off by burning or converts into energy. EPA has established an Excel-based landfill gas emissions model, which is widely used for estimating the methane and LFG emissions. It is a first-order decay equation, which is shown in this slide. As you can see, the LANGEM methane estimation model basically relies on three things: the methane generation rate, or the decay rate called K, the potential methane generation value, which is the L0, and the total waste placed. The problem addressed in this project is that the LANGEM emission results do not match with the field collected data, possibly due to the flaws in the assumptions regarding the model's independent variables. The project goals therefore include evaluating EPA's LANGEM model's coefficients, decay rate or the methane generation rate K, and the potential methane generation capacity L0. We further develop an alternate model for calculating the methane generation. The following methodology was implemented in order to meet the project goals. We collected the data for 5 landfill sites from the greenhouse gas emission reports published on the EPA website and other data sources, including the World Bank data. In the next step, the LANGEM model results were evaluated. by executing the model for at least 10 times per each landfill site by varying the category default coefficients. So that's at least 50 times the model was executed and the results were compiled. The next step, the results from the LangChain model execution were compared with the site-specific reported data for methane emissions. And by doing so, we were able to identify the best performing default coefficients and the worst performing coefficients. In the next step, we perform the parametric modeling by varying the K and L naught separately and examining the impact of that on methane emissions. In the next step, we back calculated the K and L naught values based on the results of the parametric modeling. We also evaluated the gas collection efficiency by performing a back calculation by keeping the K and L naught constant and varying the gas collection efficiency and examining the impact of that on methane emissions. Finally, we were able to develop an alternative model of methane emissions that provided promising results. We employed a machine learning model in order to perform this task. The 5 different landfill sites selected for this project are indicated on this slide.
Let's talk about some LangChain model default coefficients over here. Here you can see, based on the climate conditions, dry, wet, and moderate, the values of model K and model L naught are different. We have collected these values from the SWDC competition statement protocol over there. So we have generated 10 different models based on the different values over there, which are the different set of values. And we wanted to see what are the differences actually with the LangChain models and the reported methane value. The reported methane value actually we have collected from the EPA official website. So after calculation in the LangChain models, we have compiled the data in the Excel file. Here you can see we have put a snapshot for the Washington landfill site. One of the sites actually we have selected. So we have compiled the LangChain model data, the landfill gas, the methane generation data, and also here you can see there is a reported methane chart over here in milligram per year. So in our calculation, we have used 50% of the measured landfill gas is the methane. That's the value actually we have used. So we did the calculation and we wanted, as I have already explained earlier, we wanted to see what is the differences with the reported methane generation and the LangChain model data. So here you can see the gas collection efficiency, what's been available for the 5 different sites is just like in different values. For the CANTON Mississippi landfill site, we don't have any landfill data actually in the EPA official website. Actually, because the landfill, the CANTON landfill actually officially doesn't collect the methane generation, so there is no reported data over there. And so after calculation of the LangChain model, and we have compiled the data in the graph to have a better understanding what's happening over there. The black curve actually is the reported methane generation, and the other actually the methane generation that has been calculated from the LangChain models from different set of K and L naught. So here you can see there are differences for the landfill site that we have selected, and there is a considerable amount of difference in the inner site. So this is also a compilation of all the calculations we have done. So up to 350%, more than 350% of variation we have found in the inner site. So there is a considerable amount of difference between the LangChain model generated calculated methane generation and the reported methane that's been available in the EPA official website. This is also a compiled summary of the results what we have done, and here you can see the best result. This is the chart of the best results that we have found for different the LangChain model of one set of K and L naught, and this is the worst result. In our study for the 5 landfill sites, we have found that the K value of 0.057 and L naught equals to 102. This is the set of the value that actually gives the better result for among the 5 sets actually we have selected.
Following the evaluation of the LangChain model results, we performed the parametric modeling where we varied the K and L naught values separately and examined the impact of these changes on the emission of methane values. For Ann Arbor landfill site, for instance, uh, for a constant K, the L0 value was buried and the results were examined, and we found that for a constant K, the methane value increased by increasing the L0 value. This also increased the gap between the Langem model results and the field observed data. And for the Ann Arbor landfill value, we determined that the K value of 0.057 and L0 value of 102 provided the closest results to the observed field data. On the other hand, the parametric modeling of by varying the K value for a constant L0 value provided inconsistent results. For instance, for the Ann Arbor site, for a constant L0 value, the methane value decreased with increasing the K value. On the other hand, for the Ridgeland landfill, the methane value increased while the K value also increased.
So after the parametric modeling, we did some back calculation of the K, L0 and gas collection efficiency of the 5 different sites we have selected. So here you can see for the Washington DC, for Ann Arbor, Cathcart, Ridgeland and Canton, Mississippi, we have calculated the L0, K and gas collection efficiency back calculated values. So how we have calculated these values actually? We have done this calculation from the reported methane generation value that has been available in the EPA official website. So what we have found, there are definitely there are variation over there for the values of L0, K and gas collection efficiency. For the Washington site, we didn't find the variation of the L0, but for the other sites, we have found the variation over there for the default base weight value and the back calculated values. And same goes for the K value and the gas collection efficiency values. For the Canton, Mississippi landfill site, we don't have any landfill methane generated data. That's already we have mentioned in the earlier slides. So we didn't do any sort of back calculation over there for the Canton, Mississippi landfill. So after doing the back calculation over there, we made the average and then we have made this chart to have a better understanding of what's happening over there. Here you can see the default value and the back calculated values of L0. There are differences over there. Same goes for the K values and also for the gas collection efficiency values too. So in terms of percentage, we have found for the K up to 70% of variation with the back calculated K value and the default value. And for the L0 values and gas collection efficiency, we have found up to 51% of variation. That's, I feel like it's a great number. So we have found a great differences over there. So we have to come up with an alternative model actually to reduce the differences with the reported methane generation value and the Langem model generated methane generation. For doing that, we have come up with a machine learning model, and for the machine learning model we have to select we have selected 4 different input variables. Here you can see we have selected back calculated K, back calculated L0, organic waste composition and the rainfall data as our input variable, and as a target we have found the methane generation value over there. So why we have selected the organic waste composition and the rainfall data? That's the question actually. So in our study, what we have found, there is a considerable amount of organic waste percentage in the United States MSW landfill sites. So and also it varies with the state. Here you can see the 2 landfill sites we have selected for the as a sample. So in the Washington landfill, it's 83.86%, and in Seattle, it's 53.8%. That's a considerable amount of percentage. And in our study, we have found that in the Langem model, it's not been considered over there. So we have thought that we wanted to see what will be the impact of the Langem model methane generation if we could have incorporated the organic waste percentage over there. So also goes for the average rainfall data. Here you can see the average rainfall data from 2010 to 2020, and there are variation over there as it should be based on the states in United States. And for the 2 landfill sites we have selected in the Canton, Mississippi and Ridgeland, Mississippi, they are from the same state, so it should be 2.28. And same goes for the Washington to landfill sites. And here you can see the variation over there with, based on the states. And for our input data, we didn't use the average data. This is only for the illustration. And we have collected the individual rainfall data from 2010 to 2020 from NOAA official website as our input variable. So we have used the data of the average rainfall data and back calculated K values, L0 value. This is an illustration over there. That's what we have done. And the organic waste percentage in milligram per year we have calculated based on the available data, percentage data that's been available in the World Bank of official website. And we have calculated it from the waste in place. And then from the input data, we have calculated the target measured methane value in milligram per year. And same goes for the DC or landfill sites also. We have calculated the organic waste percentage in milligram per year, organic waste amount milligram per year from the percentage available in the World Bank official site and also in the internet from the waste in place data. And then we have used the back calculated K, back calculated L0 values, and also the rainfall data from 2010 to 2020. And then based on the input values over there, we have calculated the measured methane value in milligram per year.
Alternate machine learning based models were developed using the dataset presented in the previous slides. The dataset was split into 67% training and 33% for testing. The multiple linear regression model provided the best results among the two machine learning based models. In this equation, you can see the methane generated is determined by the various independent variables, including the waste concentration, the organic waste concentration, the K and L0 values that were determined as the best performing coefficients based on the previous evaluations, and also it considers the average rainfall. As presented in this slide, the predicted versus actual measured value correlated very well with an R-squared value of 0.99, indicating that the machine learning model was successful. We further investigated the dependency between the methane measured value versus the independent variables, and we found very good correlations, as you can see in this slide and the following slide. In summary, we can say that the best performing land gem coefficient values were not consistent among all the landfill sites. For instance, the King County, Washington site showed that the NSPS or the CAA based coefficients performed very well, whereas the Cathcart landfill, the Ann Arbor, and the Canton, Mississippi sites showed that the MRR based coefficients performed well for those sites. Whereas for Ridgeland, the inventory defaults based coefficients performed well. So when we carried out the parametric modeling by varying the K and L0 values separately, we found that for a constant L0, methane amount decreased with a decreasing K, whereas for a constant K and L0 variation, the methane amount variation trend was not consistent. For the site-specific back calculation of K and L0 analysis, we found that only the King County landfill came close to the back calculated values from the King County landfill came close to the observed field data, whereas Ann Arbor landfill coefficients were the farthest from the observed field data. We also found that by back calculation, the gas collection efficiency impacted the methane emissions considerably. Furthermore, we were able to develop a successful alternate multiple regression model that provided good methane emissions predictions with an R-square value of greater than 0.98. The independent variables considered for this alternate model were organic waste composition, rainfall, back calculated K and L0 coefficients.
So what can be the future work that can be done for the land gem model? That's what we have found. In our study, what we have found, the organic waste composition actually impacts the methane generation in the land gem model. So we recommend that there should be some value guidelines for different waste compositions over there. And also in our study and the field visit, we have found that the cover material that's been used for the landfill, the daily cover, it impacts the decomposition and also for the methane generation over there. So there should be some sort of guidelines for that too.
Furthermore, the locations and nuanced climatological conditions, including temperature and other factors, need to be considered for future work.
So thank you, everyone. That's all we have. We really acknowledge the support Dr. Sadiq Khan has given us too. He is our faculty advisor and associate professor of Jackson State University. Actually, he's the main reason that that's why we are here to participate into the competition.
We would also like to thank the industry experts, Mr. Raymond Hoffman, Ms. Rachel Akers, Dr. Bisho Shaha, and Dr. Sarah Gustitus Graham for their mentorship and the support they provided when we needed it the most.
And we also, especially we want to thank Mr. Melon Garrett actually, because for him, actually, we could have visited the Canton Sanitary Landfill. It was a great experience over there.
Finally, we would like to thank the entire SWANA organizing team for the wonderful opportunity. Thank you very much.
Thank you all.
Thank you.
So very, very good effort, good job on developing a sort of reasonable step-by-step approach to testing land gem in your alternative model. I think you kind of went quickly over the comparison to measured data. I think maybe if you could help us cover that spot portion. You have the methane flows from the greenhouse gas reports, and then you used reported collection efficiencies.
Right. So what we did was, our first challenge was to identify the actual measured methane data, which, as other teams and identified and you have pointed out, is just an estimate where we need to go by the landfill gas flow collection data that's actually measured on the field. And you take that data that's reported on the greenhouse gas emissions report on the EPA website. And then what we did was we converted that to 50% by volume to get the methane quantity in the methane volume. And then we converted that to mg per year based on the density constant. So that's how we went about getting the measured methane for each landfill site.
Okay. Yeah, one of the things here is that your work depends on those collection efficiency estimates,
right?
Which so two or three of them actually were quite high. They were at 95%, 92%.
Yes, those were reported by the landfills themselves, by the consultants, and we didn't have any reason to question them. We took it at face value and used those numbers.
Yeah.
Yeah, no, I agree that that's basically, it's a method to go by. I think we all should still recognize that they should be questioned.
Yes, they should be. And if you saw on our back calculation slide, we did back calculate the gas collection efficiency, and we found that those numbers, in order to match the collected, like the land gem numbers versus the methane measured, those numbers had to go down considerably. In one case, it was 0.7, in one case, it was 0.4. So the gas collection efficiency played a big role.
One question I had is, when you did the land gem analysis, you looked at all possible defaults rather than say, actually, all your sites except for one, well, they were all in the wet category, but 4 of them were in the very wet category. There were 2 in Washington State that were like 60 inches of rain, and 2 in Mississippi that were also very wet.
Actually, we have selected the data based on the availability because we live in the Mississippi. So we wanted to see what happens in Mississippi landfill sites. And also we wanted to see what will be the impact of the organic waste composition as soon as we have found the problem over there. So these are the 5 available sites. We have found the available data in the World Bank official website. So we have collected the data and we evaluated the results for that. That's the reason actually. So there is no any other reason why we have selected randomly these 5 sites.
Okay, yeah, no, I was asking about also the decision to go with looking at every possible permutation of the default values rather than sticking with the wet climate ones in
Yes,
your analysis.
Right, I understand your question. Yes, we didn't just try to narrow down to, okay, considering the location, go with either wet or dry. The reason we wanted to try everything was the basic assumption was the model coefficients are flawed. So let's see what are the different available coefficients, and we can try to run the model and get results. And surely enough, we did find that even though the location is wet, but the dry coefficients work well for that location in terms of coming close to the measured methane values. So what it informed us was maybe just the K and L0 values are not sufficient to get good results. So and you know, just narrowing it down based on the wet and dry category didn't give us good results. So you know, that's what we found out. But why we went that way was just, you know, we just thought, okay, let's get as much results as possible by running through all the different coefficients.
I think you have a reasonable approach because it's good to question everything. The only drawback is that you might have some offsetting errors in that if you have, for instance, the reason that your wet site does well with that L0 of 170, maybe that it should have had a higher K value.
Right.
So,
Understand.
yeah.
Yeah,
So I mean, yeah, it's a trade-off.
It is, and also the parametric. Sorry, Avipra, go ahead.
No, yeah, you can correct. I will add after that.
Yeah, I was going to say that's for the reason why we carried out the parametric modeling, where we kept the K constant. We tried with each K value, doesn't matter wet or dry. We took each K and changed the L0 and saw the impact, and then did the same with kept the L0 constant and changed the K to see the impact. So you know, that was our intention because we didn't want to get like a biased result as far as a wet K versus a dry L0 or anything like that. We checked everything with all different combinations.
And then in your solution for your alternative model, you went and you basically said, let's abandon the first order decay and let's go with a multi-linear regression.
Right.
I would think that the only problem with that is that, well, not the only, but there is a problem with that in that you have you'll have a disposal history. There's a time factor, and you have closed sites that are declining and open sites that are going up, and that your multilinear regression equation doesn't handle time and doesn't handle waste age. So that's why we stuck with the first order decay.
Yeah, it does. In terms of the waste in place, it considers the waste in place at that point in time. When we and for the closed land sites, that number is going to be high, but for a newer land site, yes, the number is going to be low. Yes, that's a drawback, which can be for in future work that can be kind of corrected. The consideration of time as also a factor into the model, and also given we only used 5 landfill sites to come up with that model, which is also not ideal, because we need to have more data, and I'm sure with more data, the results will vary.
Okay. David or Hala?
I'll just mention, again, impressive, the level of detail that you went into, the machine learning modeling, lots of work that went into that, and it was nice job. So that's the good. The not so good, I would say, is I'd be remiss to not point this out. There were a few typos throughout the presentation and the report. One in particular sort of drove me crazy, was annoying, was the King County is actually in Washington State, for what you indicated, Washington, DC. Not the end of the world, but double check your facts just when you're doing the reporting. That's all.
Sir. Yes, sir. Thank you for pointing that out. And that's something we realized during the recording of the presentation, and it was too late, and we went with the flow. But I did try to correct it in our conclusion, where we realized to be honest, something got lost in the translation between we were working, and it was DC. Although all the data is for Washington County, at some places we might have said Washington DC, but it's all for Washington County. So the data-wise, it's not compromised. The results are not compromised. It's all data for Washington County. It's just, yeah, I agree.
Understood. Like I said, not the end of the world, but
yes, thank you.
I would be remiss to not point that out.
Yes, thank you.
Any other question? We have 1 more minute.
How did you choose those independent variables in the regression, the multilinear regression? How were those selected?
So the K and L naught, we already knew they were going to be the independent variables, but the waste composition, what we found was when we increased the L naught, the methane increased. When we decreased it, so it was a linear correlation there. So we used L naught, but along with L naught, what the connected parameters are the waste composition and the organic waste composition part. So we use those two also automatically. And the rainfall, because more the precipitation, more the decay. I mean, depending on the moisture, the decomposition is more. So that's why we consider rainfall as one of the parameters.
We have more time.
We are done with the time.
Oh.
So thank you, great job to all of the students that have participated in the competition, great presentation and a lot of effort invested from all of you. Before we wrap everything for today, I just have a few general announcements. First, for the students, don't forget to visit swana.org/students for more information about the free student membership. That also it's available for access to discounts and student-focused programming. So don't forget to sign up to receive an invite to the student networking event following the design competition award ceremony tomorrow, April 6th, starting at 12 p.m. Eastern time. Also, SWANA annual scholarship program is now accepting applications due by May 2nd of this year. And for the employers listening in, make sure to visit swana.org/SWDC to access resumes for potential recruitment from this year's student teams. At the end, I would just like to thank everybody for joining and taking the time out of your busy schedules. I want to thank our sponsor one more time, the Hickman Endowment Fund, for their continued support. To the design competition, to our judges, we couldn't done this without you guys. You spend a great amount of time and effort, so we really appreciate it. Also, I want to remind you that the award ceremony will be tomorrow, April 6th, starting at 11 a.m. Eastern time. Please join us as we present the winners of this competition and also hear from the SWANA Executive Director, David Biderman. Also, as I previously mentioned, students, don't forget that after the award ceremony, there is a networking event where you can network with different solid waste professionals from varying backgrounds. You do not want to miss it. Thanks again for joining, and see you all tomorrow for the award ceremony. Thank you all.
Thank you.
Bye.
Thanks, everyone.
Thanks, everyone.
Thank you, guys.